Very good evening to all my dear students and friends. Yet another exciting topic in continuation with the series of the chemical bonding. Once again, I am back with you. In the last lecture, I explained you concept of the hybridization, why it happens, what are the electronic regions, what are the steric regions for the hybridization to happen. Last time I explained you the orbital analysis of the hybridization, how exactly hybridization index and bond angles are interlinked, what is ideal hybridization, non-ideal hybridization. Today my main focus will be a comparative study of ideal hybridization, non-ideal hybridizations, and cases of the hybridization, those compounds which do not undergo at all any kind of the hybridization. What are the reasons behind? We need to explore them. So the topic as far as is concerned is the steric analysis of the hybridizations. Let us get back to the board and try to understand the concept. Hybridization is basically of three types based on the hybridization index concept. Hybridization index, last time I explained to you, I is equal to P over S, and I explained to you a relation with the bond angle cos theta is equal to minus 1 by I. If we know the bond angle of a molecule, which is an experimental thing, which comes out to be after spectroscopic analysis, if we know the bond angle, we can find out the exact value of I. If exact value of I for a specific molecule comes out to be an integral value, then the hybridization is called as the ideal hybridizations. For example, if the bond angle is 120 degree and you just calculate the value of the hybridization index from the formula, then it exactly comes out to be I comes out to be equal to 2. That justifies that the hybridization happening is sp2. If you put the bond angle value 180 degree, then the value of I comes out to be 1. It means the hybridization is sp. If we put the value of bond angle 109 degree 28 minutes, then it exactly comes out to be 3. It means it is a case of the sp3 hybridizations. Now, based on I calculated with the help of the bond angles, the hybridization can be classified into three types. Number one is called ideal hybridization. Second case is non-ideal hybridization. And third case is no hybridization that result in the concept of the Dragos molecules. Let us get back to the board and try to understand each of these hybridization in a specific details. First of all, I am explaining to you ideal hybridization where the I is an integral value. I can have some integral values, like here it can be a 2, this can be 3, this can be 4, 5, and so on. If I comes out to be a fractional value, then it is called non-ideal hybridizations. And if I comes out to be just a minus infinity, then we say that there is happening no mixing or no hybridization is happening. Let me take here an example of methane molecules. In the methane molecule, central atom here is the carbon. And if I go for the excited state electronic configuration of the carbon, it comes out to be 2s1, 2px1, 2py1, 2p just the 2pz1. These are the atomic orbitals. Last time I have explained to you, carbon here is a tetravalent, but in this case, this doesn't undergo the bonding or the orbital overlap as such, because of the restrictions of the bond angle resulting by the hybridization in the excited state. Bond angle has to be here the 90 degree, but exactly experimental bond angle is not that way. For steric reason, bond angle needs to be increased. So in this specific case, what exactly happens, S is in a dire need of P is also in a dire need of S. Both have the mutual interest with each other, because S wants to achieve the directional property, P wants to lower its energy. And last time I explained to you that after the mixing, the resulting sp3 hybrid orbital which are found here, the resulting hybrid orbitals are just lowered in the energy. They come down from the level of the p energy level. They slightly go above the energy level of the s orbitals, but ultimately these resulting hybrid orbital achieve the directional property which make a very strong bond. So this way, in the excited state, the carbon forms here the 4 bonds, in which these hydrogen atoms are 109 degree 28 minutes apart. That is the bond angle of the molecules. Is it clear? This can also be justified if I just put the value of this, in case if I find out the percentage S character, which I last time explained to you, is equal to cos theta divided by cos theta minus 1 just multiplied by 100. If we substitute the value of the bond angle in this expression, then the percentage S character in this case comes out to be the 25%, which is in a very close agreement with the findings of the experimental result, that this carbon hydrogen bond is exactly having percentage S character equal to 25% and percentage P character is equal to 75%. If I find out the index value from here, I is equal to just P by S, this comes out exactly to be 3. So the hybridization represented, that the SPI, you just put the value of I in this expression, it comes out to be here the sp3 hybridizations. This is exactly what has been experimentally observed and what I have also achieved here by the mathematical calculations. Now let's proceed to the next case. Here the value of I came out to be exactly 3, that is integral value. That's why it is the case of ideal hybridization, and there happens a very fantastic intermixing of the atomic orbitals in this case. Let us go to the non-ideal hybridizations. For example, I am taking here the case of ammonia. In the ground state, electronic configuration is 2s2 and the 2p3. In case of ammonia, as orbital is already having 2 electrons, it is not at all interested in forming the bond. If it is not interested in forming the bond, these 3 unpaired electrons are most likely to form the bond. But if it happens in the ground state, then the bond angle comes out to be the 90 degree, because px, py, pz, these are orthogonal axes, and in case of orthogonal axis, if the bonding happens this way, then the bond angle has to be 90 degree. But the experimental findings are suggestive of the fact that the bond angle in case of ammonia is found to be 107.5 degrees. So exactly, if we try to analyze the mixing over here, S never is interested in undergoing mixing with the P. S is not at all interested because S orbital is already filled and it has not to form any bond. But in spite of its unwillingness in participation in the mixing, it takes part in the mixing. The reason is steric stabilization of the resulting geometries. Ultimately, the lone pair has to be inside that molecule, and if the molecule itself is unstable, then the lone pair will also become unstable. So exactly what happens in the ground state, there happens sp3 mixing. This is sp3 mixing. If I say that this is sp3 hybridization, so slightly it is un-okay. I'm saying that this is sp3 mixing. When I say that the sp3 mixing and when I say sp3 hybridization, these two terms are having slightly different meanings. sp3 mixing mean 1s orbitals and 3p atomic orbitals are undergoing mixing. But whether the hybridization is exactly going to be sp3 or not, that will be conclusive by just finding out the value of the hybridization index, which can be found with the help of just the bond angles. Here in this case, bond angle is 107.5 degree. If I just apply this expression over here, and a percentage S is equal to, again you can implement the same expression, cos theta. Cos theta means cos 107.5 degree over here, cos 107.5 degree minus 1 whole multiplied by 100. If we just calculate out this comes out to be somewhere around 23%. It means to say, if it is 23%, S character is if 23%, then definitely the P character will be somewhere around how much? 77%. So if I find here the hybridization index I, that is 77 over here 23, so this is going to be something around 3 point something. It means it will come out to be a fractional value, and if it comes out to be the fractional value, it means hybridization that has happened is non-ideals. Why exactly non-ideal hybridization happens in this case? The reason for this is very explicit, because lone pair is not interested in mixing with the p orbitals. P orbital is very much interested in being mixed with the S, because due to static reason it wants to expand the bond angle from 90 degree to the higher value, that in this case is 107.5 degrees. So in order to fulfill the need of the p orbital, S sacrifices some of the S character towards the P, and as a result of this, because S is not fully involved in the mixing process, most of the percentage S character is retained by the S orbital itself, and that is the reason why in this case complete mixing has not happened. Therefore, this is a case of partial mixing, and if it is a case of the partial orbital mixing, then definitely I will not come out to be an integral value. It will be somewhere a fractional value. That is why it is called here non-ideal hybridizations. I think this is understandable to just all of you. Percentage S character here is 25, and percentage S character in this case and percentage S character in the bond. In the bond, I have calculated this to be the 23%. 23 plus 23 plus 23, if we just add them up and just subtract from just from 100, so you can also find out the percentage S character that is lying in the hybrid orbitals. Is it clear? So here percentage S character in the hybrid orbital will be comparatively higher. If I add them 23 times 3 3s are 9, 3 2s are, that is 6, and out of 100 minus this comes out to be 31%. It means to say the percentage S character here is somewhere around 31%, and we know that very well that the percentage S character is directly related to bond angle theta. Bond angle theta directly to the percentage S character. But exactly this is not here a bond as such, because lone pair doesn't form here the bond. Is it clear? So percentage S character in the hybrid orbital is higher. That's why the percentage S character in the bond is less. And if it is less, then definitely bond angle will become smaller. And if the bond angle is smaller, this is in a close agreement with the observed fact here. Very, very interesting case is this one, the phosphines. Just down the group after the nitrogen, we come to the phosphorus. If it forms the hydride with the hydrogens, it is the pH3. It is expected that it has its structure and its hybridization has to be like this, but exactly it is not the situation here. What exactly happens in this case, if we go for the ground state electronic configurations, the ground state electronic configuration is your 3s2 3p1. Is it clear? In this very strange situation, it's a very, very interesting situation. S orbital is already filled, just already having 2 electrons. It is not interested in the bonding. Just as in case of ammonia, it was not interested, but due to steric reason, it participated in the process of the hybridization. In case of the phosphines, S is not at all interested in mixing with the p orbitals. But here a very strange situation is that here P was interested in getting mixed with S. But in this very case, P orbital is also not interested in mixing with the S orbitals. If S is not interested in mixing with P, P is not interested in mixing with S, it means the net result will be no hybridizations. And if there is no hybridization, then the S orbital of the 3 hydrogens will straight away undergo overlapping with the px, we have pz orthogonal axis oriented orbital, resulting in the formation of bond angle close to 90 degree. Not exactly 90 degree, but just it is very close to the 90 degree. And if it is close to 90 degree, and you substitute in this case, if the bond angle is 90 degree, and you just try to find out the value of cos theta, exactly last time I told you is equal minus 1 divided by, that is I. If you find out the value of I from this, just put the value of theta to be the 90 degree. Cos 90 inverse comes out to be just here the negative infinities. And if I comes out to be here the negative infinity, this implies that there is no hybridization. Now the question arises, why exactly hybridization has not happened in this case? This is a mathematical interpretation that I came out to be the negative infinity, but the question here arises, why exactly hybridization theoretically doesn't happen in this case? In order to explain this, Let me come back here and just try to understand here a very interesting situation in case of the pH 3. Actually, what happens in case of the pH 3 and the NH3 I am taking for comparison. For example, in case of the nitrogen atom, let me take the size of the nitrogen atom this much, and this one is here the phosphorus atom. Let me take the size of the phosphorus atom just like this. If nitrogen doesn't participate in the process of the hybridization, since the size of the nitrogen atom is comparatively smaller, and for example here at the 90-degree, it has to form the bond. It has to undergo overlapping with the two hydrogen atoms. So hydrogens orbital I am showing by this much of the size. These are s orbital of the hydrogens. And if in this process a bonding happens, then these hydrogen will be very close, and if they are close, there will be a great steric repulsion in them. So in order to minimize the repulsion, here the mixing happens, because when S character gets mixed with the p orbital, then this bond angle increases. As S character increases, then what exactly happens? Bond angle will also increase in this case. Now let me come back to this situations. In case of the phosphorus, which is pretty big in size, if it undergoes overlapping in the ground state as such, this is the hydrogen atom, this is the hydrogen atoms. Here exactly steric stabilization is not needed, because these two hydrogen atoms already are far apart from each other, and here even at the 90-degree there has already come out the steric stabilizations. If there is already steric stabilization at the 90-degree, therefore p orbital do not have any demand from the s orbital to get mixed up, and that is the reason here sp3 hybridization has not happened. Is it clear? If I take another very important example, one interesting example I am taking, this is the story of ammonia, where sp mixing has to happen. In case of the pH 3, sp mixing is not required because already steric stabilization is there. If I take an example of another compound PF3, let us understand this case. This is again here a phosphorus atom, and let me again take here, these here the fluorine atoms. Let the fluorine atom, I am just showing for the sake of just interpretation. I am showing the fluorine atom just like this. The fluorine atom, it is also the fluorine atoms. In this case, the hybridization comes out to be, and mixing sp3 happens in this case. In this case, there is no sp3 mixing, no sp3 hybridizations. Now exactly what happens in this case, this phosphorus is bonded with the 3 fluorine atoms, and fluorines are highly electronegative. They will put partial positive charge over to the phosphorus. There will happen the charge contractions. If the charge contraction happens, as I told you, if the one fluorine gets bonded, this will put a positive charge over here. If positive charge comes over to the phosphorus atom, its size will squeeze. Let me, for example, say if one fluorine gets bonded with the phosphorus, what exactly will be the result? One fluorine atom is reducing the size of this fluorine atoms from this much. For example, the size has become this one. When another fluorine gets bonded, the size will get further reduced. Size has become just further reduced. The third fluorine is coming, the size again gets reduced like this. So if finally I try to understand this situation, now what exactly has happened? The phosphorus atom has got reduced into a very small size, and now these are the fluorine atom which are bonded here. One fluorine atom, another fluorine atom. What exactly will happen? Due to a smaller size of the phosphorus atom, again what will happen? There will become a steric repulsion. It means the molecule will tend to become unstable due to very high steric repulsions. So in order to minimize these repulsions, here these s orbital of the phosphorus, s orbitals, these are the p orbitals, it is filled, this is singly occupied. How exactly this angle can be increased? This angle can only be increased if p orbitals get mixed with the s orbital. So if the mixing happens, again here the hybridization comes out to be sp3. Because of the decrease in size of the phosphorus atom, fluorine have come very close. Now these fluorine want to go far apart in order to stabilize the molecule sterically, and for that it will have to increase its bond angle, and bond angle can only be increased when s orbital gets mixed with the p orbitals. If the p orbital do not mix with the s orbital, then the bond angle has to be 90 degree. By mixing with the s orbital, again it will tend to increase its bond angle, and in this case bond angle comes out to be 102 degree approximately. So that is the reason, and from here comes a concept of the Drago's rule. What exactly is the Drago's rule? Drago's rule is being implemented over here in this case, and the molecule as such is called as the Drago molecule, Drago rule. What exactly is the empirical statement of the Drago's rule? It says that if the central atom, I am just, you can make the definition keeping this in your mind. If the central atom belongs to third period, P3, P4, P5, P6, just like this. If the central atom belongs to third period and onward, and the side atom and the side atoms are essentially hydrogens. Hydrogens mean electronegativity is less than 2.5. Electronegativity on the Pauling scale for the hydrogen is 2.1. If central atom belongs to third period or onward and the side atom has electronegativity equal or less than 2.5, then in such a situation there happens no sp mixing in the central atom, meaning there happens no hybridization in the central atom. This is exactly the Drago's rule. And if this is the case, if no sp mixing is happening, then what will happen to this lone pair? This lone pair will still remain in the 3s orbital, and s orbital, they are very close to the nucleus. There will be a very, very strong hold on the s electrons, and these s electron will become stereochemically inactive. Stereochemically inactive means the lone pair of electron, which is essentially present in the s orbital and is not involved in the usual chemical bondings. Stereochemically active lone pair are those which are present in the hybrid orbitals, and they can result in the formation of bond. Is it clear? So this is the empirical statement of the Drago's rule. That is, once again I am telling, if the central atom belongs to third period or onward and the side atom has electronegativity equal or less than 2.5, then in such situation central atom doesn't undergo any hybridizations and lone pair of the electron in this case remains purely in s atomic orbital and it becomes stereochemically inactive lone pair. I hope this concept of ideal, non-ideal, no, and the case of no hybridization must have been explicit to you. The Dragos molecules, other example, the phosphine, arsine, bismuthines, these are the other example, stebines. Likewise, it happens in the oxygen family as well. Except oxygen, if we just go downward, H2S, H2SE, H2T, these are examples of the Dragos molecules. The Dragos rule has come after the steric analysis of the phosphines. Steric analysis I did with the PF3 phosphorus trifluoride, where the fluorine being the side atom, being more electronegative, they just exalted the positive charge on the central atom, which resulted in the contraction of the size of the central atom, which brought the two fluorine very close to each other, resulting in steric repulsion. And in order to minimize that, they will have to go far apart. For that, the bond angle needs to be increased, and for this purpose sp mixing has to be there. Hopefully you might have understood this concept. Thank you very much and wish you all the best.